Imagine that you're traveling at 60% the speed of light.
What would you look like to someone on Earth?
You'd just look the same, right?
Wrong.
Hi, I'm Ketzel.
And I'm Miriam, and we're here to talk about Bell's paradox, initially proposed in the 1950s.
In this paradox, there are two spaceships connected by a rope of set length who are accelerating at the same rate. From Earth, the distance between these two ships stays constant.
At first, it seems like there's no paradox here, because as they accelerate at the same rate, the distance between the two spaceships remains constant, allowing them to fly off into the galaxy together.
But this isn't true. The rope has to break. Why? Let's talk about that.
There are a couple basic principles that we need to define before we dive into the paradox. First, we need to talk about reference frames. Imagine you are traveling at a constant velocity in a train without windows. To you, everything is at rest. Any other person, box, or stick of dynamite in that train car with you will appear to move around in a stationary space. Now put windows in your train car. All of a sudden, you can see plants, people, and animals all passing by. However, as far as you know, you're still at rest. It's simply the outside world that's moving. Within an inertial reference frame, everything is at rest to you in that frame. So the train car is one reference frame, and the ground or earth outside the train is another frame that is not at rest relative to you. In our paradox, there are two reference frames. One frame is from the view of someone on Earth watching the two spaceships flying by, and the second is from one spaceship's frame watching the distance between itself and the other ship. From both frames of reference, the rope must break.
Another term to define is proper length. The proper length of an object is whatever the object's length is in the frame that you are observing from. In classical mechanics, an object's proper length is just its length, but once things start moving close to the speed of light, things get a bit more complicated. The reason that we have to specify proper length is due to a key principle of relativity known as length contraction. In essence, length contraction means that if an object is traveling very, very fast relative to you, its length in your frame of reference is shorter than its proper length. The amount that the object contracts is proportional to how fast it is traveling relative to the observer, as seen in this equation. It's important to note that this isn't just some optical illusion. The object's length is actually different in different reference frames. The reason why this occurs is rather complicated, but at its core it is due to the fact that c, the speed of light, is constant in all reference frames.
In the first reference frame, someone at rest on Earth watches as the spaceships fly by, let's say hypothetically at 60% the speed of light. Thanks to the property of length contraction, the rope between the two spaceships seems to contract, but as stated in the problem, the distance between the ships stays constant in the Earth reference frame. Thus, the rope is now shorter than the distance it has to span, and it must break.
So that explains why people on Earth see the rope break. But in the spaceship frame, the rope doesn't contract and remains its proper length, so why does an observer on the spaceship also see it break? This is because the rope isn't the only thing that is affected by length contraction. It's important to remember here that length contraction isn't the result of objects or atoms being squished together, it is literally space pushing closer. At relativistic speeds, both the length of objects and the distance between them contract. Because of this, at point 6c, the empty space between our two spaceships also contracts. If we return to our paradox, we see that the distance between the ships is constant, as seen by an observer on Earth. But because the spaceships are moving relative to Earth, that observed distance is in fact contracted from the proper distance between the ships. As the ships speed up, in order for their contracted distance to stay the same, the proper distance must increase as well, because contraction is proportional to velocity. This means that while the rope stays the same length, the distance it spans increases, and so it breaks.
To sum up, the rope breaks from the Earth's perspective because it contracts across a constant distance, and from the ship's perspective it breaks because the rope length stays constant across a growing distance.